This is second module of the 7th chapter. In this module, we discuss prime elements and irreducible elements of a commutative ring R with 1. Prime elements are the generalizations of the prime integers. Then, what is the irreducible element? Recall the definition of prime integers. An integer p greater than 1 is defined to be prime if it has only two positive divisors 1 and p, whereas its equivalent condition is that an integer p greater than 1 is prime if and only if whenever p divides a b, then p divides a or p divides b. If you look into the definition of prime integers, then you see that an integer p greater than 1 is defined to be prime if the divisors of p are either units or associates of p. Though in Z the definition is equivalent to the condition p divides a b implies p divides a or p divides b, but these two are not equivalent on an arbitrary commutative ring R with 1. That is why, as a generalization of prime integers on a commutative ring with 1, we get two notions, one is prime element and the other is irreducible element. Thus, we define prime and irreducible elements as follows. Suppose R is a commutative ring with 1, then we define a non-zero non-unit element p of R to be irreducible if for every a b belongs to R, p equal to a b implies that either a or b is a unit. And naturally, we will define p to be reducible if p is not irreducible. And we define a non-zero non-unit element p to be prime if for every a b in R, p divides their product implies that either p divides a or p divides b. First of all, we give two elementary examples, one of irreducible element and other of prime element. Consider 7 in Z, then 7 has only two factorizations, namely 7 cross 1 and minus 7 cross minus 1. In these two factorizations, we have 1 and minus 1 which are units. Thus, 7 has no factorization as a into b in Z such that neither a nor b is a unit, and hence we conclude that 7 in Z is an irreducible element. Now, consider minus 7 from Z. If minus 7 divides a b, then we have 7 also divides a b, and since 7 is a prime integer, either 7 divides a or 7 divides b, which implies that minus 7 divides a or minus 7 divides b. Thus, minus 7 is a prime element in Z. Here you note that minus 7 is not a prime integer. By definition, prime integers are all greater than 1. But if we consider Z as a commutative ring with 1, then we have minus 7 is a prime element. Note the difference prime element and prime integer. Then it is my responsibility to show that there are elements which are irreducible but not prime, and elements which are prime but not irreducible. First, we give an example of an irreducible element which is not prime. For this, consider the integral domain z I root 5 and the element 2 plus I root 5 in this ring. To test the irreducibility, assume that 2 plus I root 5 is a product of the elements a plus ib root 5 and c plus id root 5. Then it follows that a square plus 5b square into c square plus 5d square equal to 9. Since 9 has only 3 factorizations, namely 1 into 9 and 3 into 3 and 9 into 1, we get either a square plus 5b square equal to 3 and c square plus 5d square equal to 3, or a square plus 5b square equal to 1 and c square plus 5d square equal to 9, or a square plus 5b square equal to 9 and c square plus 5d square equal to 1. Note that there are no integers a, b, c, d which can satisfy equation 0.1, and from equations 0.2 and 0.3 it follows that a plus ib root 5 equal to plus minus 1 or c plus id root 5 is plus minus 1, which implies that either a plus ib root 5 is a unit or c plus id root 5 is a unit in z I root 5. Hence, it follows that 2 plus I root 5 is an irreducible element in z I root 5. Now, we show that this element 2 plus I root 5 is not prime. For this, note that 2 plus I root 5 into 2 minus I root 5, this product is equal to 9, which can be decomposed as 3 into 3's, and hence 2 plus I root 5 divides 3 into 3. But we see that 2 plus I root 5 cannot divide 3. If on the contrary 2 plus I root 5 divides 3, then 3 is a multiple of 2 plus I root 5, say 3 is equal to 2 plus I root 5 into a plus ib root 5 for some a plus ib root 5 in z I root 5, which implies that 3 is equal to 2a minus 5b and a plus 2b equal to 0. These two equations together implies 3 is equal to minus 9b. Since b belongs to z, this cannot be. Hence, our assumption that 2 plus I root 5 divides 3 is wrong. Thus, it follows that 2 plus I root 5 is not a prime element in z I root 5. Thus, 2 plus I root 5 is an irreducible element, but not a prime element in the integral domain z I root 5. Now, I give an example of a prime element which is not irreducible. For this, consider the ring Z6 and element 3. Since the notion of irreducibility relates units, so first identify the units of Z6. Note that in Z6 there are only two unit elements, namely 1 and 5. Here we see that 3 is equal to 3 into 3, and since 3 is not a unit in Z6, we see that 3 can be expressed as a product of two non-unit elements, and hence 3 is reducible, that is 3 is not irreducible. Now we show that 3 is a prime element in Z6. For this, consider box A and box B in Z6 such that 3 divides AB. Then AB is a multiple of 3, that is AB is equal to 3 into C for some C in Z6, which implies that 6 divides AB minus 3C. Then 3 divides AB minus 3C, and hence 3 divides AB. Though we are considering here Z6, still the relation 3 divides AB is in Z, because all these 3 elements 3, A, B are in Z, and since 3 is a prime integer in Z, so it follows that either 3 divides A or 3 divides B, which in turn becomes box 3 divides box A or box 3 divides box B in Z6, and hence 3 becomes a prime element in Z6. Thus, we see that in a commutative ring R with 1, in general there are elements which are irreducible but not prime, as well as some elements which are prime but not irreducible. Now, it is natural to ask, can we give a condition or a set of conditions on a commutative ring R with 1 so that every prime element will be irreducible or every irreducible element will be prime? For this, we see that if R happens to be an integral domain, then every prime element will be irreducible. Thus, we show that in an integral domain every prime element is irreducible. To prove this, consider an integral domain R and a prime element P in R. We show that P is irreducible. For this, suppose P is equal to BC, where BC are in R. Then P divides BC, and since P is prime, it follows that either P divides B or P divides C. If P divides B, then B is equal to P into some element Q in R. Then we have from P equal to BC that P is equal to PQC, and so P into 1 minus QC is equal to 0. Since here we have assumed P to be an irreducible element, and by definition every irreducible element is non-zero, non-unit, so P is non-zero. And since R is an integral domain, it has no zero divisor. So, from the identity P into 1 minus QC equal to 0, it follows that 1 minus QC is 0, and that is QC equal to 1, which shows that C is a unit. Thus, if P divides B, then we have C is a unit, and similarly if P divides C, then B is a unit. Thus, it follows that either B or C is a unit whenever P equal to BC, and hence P is an irreducible element in the integral domain R. Now we discuss interrelations between prime elements, irreducible elements and prime ideals, maximal ideals. In Z, we see that an ideal NZ is a maximal ideal or a prime ideal if and only if P is a prime integer. So, what happens in case of an arbitrary commutative ring R with 1? Here we show that the prime elements directly associated with the principal prime ideals, but the case for irreducible elements and maximal ideals is not so simple. Now, we show that if P is a principal prime ideal, then its generator is a prime element and every prime element generates a prime ideal. For this, first assume that P is a prime ideal of R. Since P is a prime ideal, by definition it is proper and hence its generator P cannot be a unit. Also, we assume the ideal P to be non-zero, hence its generator is non-zero. Thus, the generator P is non-zero non-unit. To check that this generator P is a prime element, consider two elements A and B from R and suppose that P divides AB. Then the product AB belongs to the ideal P, which implies that either A belongs to P or B belongs to P, since P is a prime ideal. And since the ideal P is generated by P, it follows that A is a multiple of P or B is a multiple of P, that is P divides A or P divides B. Thus, it follows that the generator P is a prime element. For the converse, suppose that P is a prime element. Then from the definition of prime elements, it follows that P is non-unit, and so the ideal generated by P, which we denote here by P, is a proper ideal of R. Now, to prove that this ideal P is a prime ideal, consider two elements A, B in R and assume that their product A, B is in P. We are to show that either A belongs to P or B belongs to P. For this, note that the ideal P is generated by the prime element P, and since AB belongs to the ideal P, so AB becomes a multiple of the prime element P, that is the prime element P divides AB. And since this is a prime element, it follows that either P divides A or P divides B, that is either A is a multiple of the prime element P, in which case A belongs to the ideal P, or B becomes a multiple of the prime element P, in which case B belongs to the ideal P. Thus, we get either A is in the ideal P or B is in the ideal P, and hence P becomes a prime ideal of R. There are examples of principal maximal ideals. which is not generated by irreducible elements, or there are elements Q which are irreducible, but the ideal generated by Q is not maximal. But we have a consequence. If D is an integral domain and M is a principal ideal generated by Q becomes maximal, then the generator Q is an irreducible element. For this, note that every maximal ideal by definition is a proper ideal. Hence, the generator Q of M cannot be a unit. Also, as we have assumed M to be a non-zero ideal, Q is also non-zero. Thus, Q becomes a non-zero and non-unit element of R. To prove that Q is an irreducible element, consider two elements A and B from D and assume that Q is product of AB. To prove irreducibility of Q, we ought to show that either A is a unit or B is a unit. Now, since Q is a multiple of A, so Q belongs to the ideal generated by A. Again, Q is a generator of M, hence M becomes a subset of the ideal generated by A. Since M is a maximal ideal, it follows that either the ideal generated by A is equal to M or the ideal generated by A is equal to the whole ring D. If it is equal to M, then A belongs to M, which shows that A becomes a multiple of Q, that is A equal to QC. Replace the value of A in Q equal to AB and we get Q equal to QCB. Since Q is non-zero and D is an integral domain, it follows by the cancellation law in D that 1 is equal to CB and hence B is a unit. Thus, if M is equal to the ideal generated by A, it follows that B is a unit. Now, if the ideal generated by A is equal to D, then 1 belongs to A, which shows that A is a unit in D. Thus, either A is a unit in D or B is a unit in D, and hence it follows that Q is an irreducible element. Now, we show that if we consider a ring which is not integral domain, then it may be that the ideal generated by Q is maximal, still Q may not be an irreducible element. For this, consider the ring Z6. You all know that Z6 is not an integral domain, and the units in Z6 are 1 and 5. These two are the only units in Z6. Now, consider the ideal M generated by 3, then this is a maximal ideal, but 3 is equal to 3 into 3 shows that 3 can be expressed as a product of two non-units, and hence 3 is not an irreducible element in Z6. Thus, if we take R to be non-integral domain, then ideal generated by Q may be maximal without Q being an irreducible element. Now, we show that the converse of the above result does not hold. That is, even if we are in an integral domain, we show that irreducible elements may not generate a maximal ideal. Here, for example, we consider the ring R as the polynomial ring over Z, that is over the ring of all integers. Then it is easy to prove that X is an irreducible element of R. Let us see. Suppose X is a product of two polynomials f(x) and g(x) in Zx. Since Z is an integral domain, so it has no divisors of 0, and hence it follows that degree of x is equal to degree of f(x) plus degree of gx, that is 1 is equal to degree of f(x) plus degree of gx, since Z is an integral domain, which implies that either degree of f(x) equal to 0 or degree of gx equal to 0. If degree of f(x) equal to 0, then f(x) equal to a belongs to Z, and so x becomes a into gx, which implies that a into b1 equal to 1, where b1 is the coefficient of x in gx, and thus a equal to f(x) becomes a unit in Zx. Thus we see that if x is a product of f(x) and gx, then either f(x) is a unit or gx is a unit, and hence x is irreducible. Now we show that the ideal generated by x is not a maximal ideal. This is very simple to observe, that Zx by ideal generated by x is isomorphic to Z, but Z is not a field, and hence the ideal generated by x is not a maximal ideal. Thus we see that the case for the irreducible elements and maximal ideals is not so simple. Thus we introduce two notions, namely prime elements and irreducible elements, on a commutative ring R with 1, and both these notions are generalizations of the notion of prime integers in Z. In Z, these two notions are same, but we have examples of irreducible elements which are not prime, and elements which are prime but not irreducible. So, on an arbitrary commutative ring R with 1, these two notions are different and independent. Though we have a result, if R happens to be an integral domain, then every prime element is irreducible. In the next module, we characterize the rings where every irreducible element becomes prime, and there we give the exact reason why in Z these two notions coincide.